So let's look at an example. So here's a vector field. F is y cubed, comma, minus x cubed. And we want to integrate, do the line integral on C, which is a positively oriented circle of radius 2 centered at the origin. So what does that mean? We have a radius 2, and we're going the usual way, counterclockwise way. Okay, so before we had Green's theorem, we would have to do it this way. It's f dot dr, where r is some parameterization of C. So that's not too hard. Parameterization can be 2 cosine t, comma 2 sine t, and we know that going once around the circle, t goes from 0 to 2 pi. Everything's vanilla and nice. Okay, so let's do this, or try to. Okay, so we're going from 0 to 2 pi. F, now we've got to plug in r into f over here. So this is actually going to be 8 sine cubed of t, comma, and this is negative 8 cosine cubed of t. Okay, dotted with dr, which was r prime of t dt, right? So we need to take a derivative. So this is minus 2 sine t, comma, positive 2 cosine t dt. Okay, now I calculate the dot product. Let's see what happens. This is minus 16 sine to the fourth of t. This is what I get by multiplying the x components. Oh, not comma, but plus, or in this case minus, because this thing is negative. Minus 16 cosine to the fourth of t dt. Okay, now this is tough. Sine to the fourth of t and cosine to the fourth t are both a little bit annoying to integrate. You can do it. You use the double angle formula twice. But maybe there's an easier way. And also, you have no idea, so certainly you can try, but you have no idea when you're evaluating a line integral, when you get to this point, what this function is going to look like. So this function could be something that's literally impossible to integrate. Like you could have gotten the integral of e to the t squared dt. That is literally impossible, at least to evaluate without a lot more advanced methods. So Green's theorem can help with that if you get something either difficult or impossible to integrate. So let's see, we have a circle of radius 2, so like everything's very, very nice about this. We can certainly check all the conditions. Let's see. Okay, it's a region in R2. We're defined on all of D. There was nothing wrong with the y cubed comma negative x cubed. It's certainly, the components have continuous first derivatives. That's great. The boundary is a circle, so it's definitely it's in fact just a smooth, simple, closed curve. So it's certainly a union of piecewise simple, smooth, closed curves. And the region can certainly be composed by adding those curves. And it's simply connected. Okay, so everything was nice about it, which we probably suspected starting with a circle. Okay, so Green's theorem applies. And then, so instead of doing all this, we can actually do, we can integrate over the region D, which is the interior of the circle. Okay, so let C be the boundary of D. So now we have the region D, and then we need, let's see, Q x minus Py dA, right, where Q is negative x cubed, and P is positive y cubed. Okay, so let's just do that. So we're integrating over the circle of radius 2 centered at the origin. Partial derivative of the second component with respect to x is negative 3x squared, minus partial derivative of the first component with respect to y is 3y squared. And now we're integrating over a circle of radius 2. Okay, this is very easy to do in polar coordinates, so let's switch to those. So this is minus 3r squared. R squared is x squared plus y squared. We need an r dr d theta. And then we just have r going from 0 to 2, and theta going from 0 to 2 pi. Okay, so this is easier to do than what we had, 0 to 2. Just go ahead and quickly calculate it, minus 3r cubed dr d theta. So that's 0 to 2 pi, and this is minus 3/4 r to the 4, sub in 0 to 2 d theta, and then let's see, 2 to the 4 is 16 divided by 4 is 4, so minus 12 minus negative 0 is easy, d theta, so that's negative 12 theta going from 0 to 2 pi, and we get an answer of negative 24 pi. What does that mean? That means if you did this amount of work walking around this circle this way, that was actually a net negative amount of work. You lost energy somehow. Okay, cool. So those who like doing this kind of thing, you're welcome to try this one and make sure it comes out to the same thing. But otherwise, you can just trust that Green's theorem works.